So for this first video, I'm going to just give an overview of what you need to know for the Affine term structure models part of the course. This is really important because it consists about like a third of the points for each of the exams. So I'm going to just give an overview. So first off, it's used for modeling short-term interest rates, which is shown to be as RT. There's 6 different equations you need to know. So 4 of them are Vasicek and 1 of them is CIR. So right here, you can see each of the equations, which you don't need to memorize. So you see here, there's 3 discrete equations and 3 continuous that you need to know. So for the single factor Vasicek models, you have these 2. You see that these equations are quite similar. You see the lambda t equation is exactly the same. And then here you see for the short-term interest rate part, it's very, very similar. You see here just a delta RT and here's a DRT, and that's just because for the continuous case, it's they use it because it's like the DRT part is just close to 0. You see the rest is pretty similar, but for the continuous case, you use stochastics, and here you just show the noise. So the stochastic part just replaces what was shown as noise. And then for the stochastic discount factor, we use this M equation for the discrete and these uppercase lambdas. Instead, the rest equation is fairly similar. For the single factor CIR, so the CIR stands for Cox, Ingersoll, Ross. So this is almost exactly the same, but they add these square root RT terms into parts of it. That's the only difference between this one up here. So it adds kind of a more time varying component. For the multi-factor Vasicek model, this is a bit more tricky. Here we have to use linear algebra to do the derivations. You can see those equations here. Let's see, moving on. So these are the methods to solve each of these. So for the discrete time solution, you need to know these 4 steps. So first off, you start with assuming the solution, and then you need to show that both the stochastic discount factor and the price equation, that they're both log normal. Then you need to apply the discrete time no arbitrage condition, and then you need to obtain A and B. This is a fairly simple process, but it just takes a bit of time. For the continuous time solution, it's quite a bit more lengthy, so the overall steps are pretty similar. You see the steps 1, 3, and 4 are exactly the same, and then the way to get to the no arbitrage condition is a bit different. You have to come up with this, which takes a bit of derivation, but it's not that hard math. And then you have to use the continuous time no arbitrage condition, which is a bit different from the discrete time. So the equations you need to know. So for the discrete time, there's just one equation that you need to know. That's quite simple. You see here, you take the expectation of this and you take 1/2 of the variance of the same equation. So it's fairly straightforward. For the continuous time case, there's 3 different equations you need to know. So first off, you have to do this Ito step. Then you need to do this step, which I don't know if it has a name. You see here that this Ito part is used right here. And then you apply the no arbitrage condition. And you see this right here is put in right here and right here. Whereas these other parts, this and this, they're just given. So this is just straight math. And then at the end of each of these, you will get an equation that looks like the assumed solution right here. And then you find the A and B values based off of what doesn't have a RT component or what does. So you see right here. Let's see, a couple other things to note. In a lot of these equations, you see that there is a lot of t's, taus, and lowercase t's. So you see here, uppercase t, tau, and lowercase t. All of these, it's not me just making a mistake. These are intentional, so these are very different. Also, these d's and the deltas, they are also different. So make sure not to assume they're the same.